Hi, this is a new video part of the research project Analog Spiking Neuron Model for Unsupervised STDP-based learning in Neuromorphic circuits for my master thesis. I am going to talk about the project today. I wanted to do a short introduction to neuromorphic systems. So why is it a subject currently raising considerable attention? Well, as you may know, artificial intelligence has demonstrated remarkable success in solving complex problems. So AI is often achieving or even surpassing human-level performance in various intelligence-required tasks. So you may have heard of AlphaGo, which had beaten Lee Sedol in 2016, who was considered as the best Go player. I'm sure you've also heard you've probably even tried recent generative AI such as Midjourney or ChatGPT. So those AI provide absolutely incredible results, but those success often come at a much higher cost in terms of database and also in terms of energy consumption compared to human. In fact, AlphaGo would have a power consumption of around 1 megawatts, where Lee Sedol, who is a human, would have a brain consuming around 20 watts. And what about ChatGPT? Well, I do not really like the comparison. I mean, I've seen this example in few presentations, and I do not really agree because we should compare what is comparable. And ChatGPT has learned a significant part of the entire internet, and it can do what would require many lives or many healthy human brain. And so we can't really do the comparison. It would be, for me, it would be like compare a bus to a human for going from a place to another place. So of course the bus consumes much more energy than the human, but it can also do much more than the human. So the comparison, of course, is possible, but it would require much more arguments rather than just say that the human brain is 20 watts and ChatGPT is I don't know, but a huge amount of megawatts. In fact, the increasingly complex implementation of artificial intelligence often runs on traditional von Neumann architectures. And von Neumann architectures are limited by the performance gap between CPU and memory. So this is known as the memory wall. So the processor has to wait for multiple clock cycles in order to receive the data from the memory. And also the information travels constantly between CPU and the memory through buses, which consume a lot of energy. Those accomplishments come at a substantial cost in terms of energy consumption, and which limit the widespread applications of AI. For embedded system, for instance, where energy consumption is absolutely crucial. Supercomputer Fugaku is a very good example to illustrate why it's not a good idea to emulate the brain functioning with traditional computer architecture. I took the example from a presentation of Simon Thorpe. So the supercomputer Fugaku would have a capacity of around 500 petaflops for a power consumption of around 30 megawatts. And calculating the brain states with a millisecond precision would cost around 600 petaflops. But it is done with only 20 watts for human, with a much higher precision. So it really highlights that it would be the wrong way to build a huge supercomputer to emulate the brain, a brain at least. Hence, a bio-inspired solution would be required here. And here comes the neuromorphic architectures. So, therefore, neuromorphic hardware and computation gained significant attention as a potential solution, drawing inspiration from the structure and the function of the mammalian brain. Obviously, even with the progress of AI, the human brain still stands out for its exceptional capabilities. It contains approximately 86 billion neurons, of which less than 1% are active simultaneously, with an average frequency of spike per neuron below 10 Hz. leading to a low power consumption of around just few tenths of watts, according to Azevedo, Javes, and Lenny right here. I will provide the DOI at the end of the presentation. So, by replicating the differential equation governing neurons and synapses behavior through analog circuits, neuromorphic systems can achieve power consumption reduced by several orders of magnitude compared to numerical solution of this equation using digital processors. Here, Loihi is a neuromorphic chip developed by Intel, and it enables 100 times less energy consumption compared to GPU, according to Blow in 2019. So Loihi, however, here Loihi isn't a fully analog neuromorphic circuit replicating differential equation through its intrinsic behavior. So it has an energy consumption per synaptic spikes of around 23 picojoules, where analog circuits from the states of the art consume in femtojoules per spikes. So you can find some explanation about analog circuits in FERA in 2019, from 2019. I won't go any further for this field. But with analog circuits, the power consumption can be lowered by like 10,000 from the current state of the art. It can be lowered by around 10,000 order of magnitude. So it's a very a subject draining a huge attention. Neuromorphic architectures are composed of numerous neuron equivalent processing elements connected by synapses. Significant enhancements in power efficiency and latency for a broad spectrum of computational tasks could be yielded for several reasons. So here I provide a non-exhaustive list. And so first, it has SNNs as an asynchronous and highly connected and parallel event-driven computational model with processing elements transmitting information through spikes, and so consuming energy only when required, because spike is all or nothing, and so consume only when there's spikes, and only and thanks to the event driven, it does consume only when required. Plus, the collocation of storage and computation reduces the need for continuous communication between memory units and processors, known as a limit in von Neumann machines, as I explained just before. Also, SNNs have been theoretically demonstrated to be at least as powerful as ANNs by mass in 1997. And also, spikes have a binary state, as I said. So there's a spike or there's no spike, and there's no information into the magnitude of the spikes. So this information is easier to convey between processor units if you have multi-processor units, like in the Loihi chip. So information is easier to convey between processor units rather than if it was scalar value related to ANNs. Finally, I wanted to broaden the vision of neuromorphic systems and neuromorphic computing, because it's not only beneficial for artificial intelligence, because it mimics the brain functioning in a higher degree and use spikes as the brain does. We could say that neuromorphic systems speak the language of the brain, and hence it can be used for rehabilitation implants, for instance, or for a brain chip or other chip with a bilateral connection and bilateral communication with biological neurons. And so yeah, it's a very interesting field. Also based on event-driven and asynchronous processing. So event-driven, as I said before, means processing information only when there's new information to process. And so based on these methods, some specific cameras can achieve a high precision recording with low power consumption in embedded systems. And here I provide an amazing example. So we can see the precision of the cameras from Prothesis. prothesis. So with a low consumption, they achieve to have a high precision and a high quality in the video. And yeah, this is based on event driven. And if you want to watch more video about that and more explanation about that, just feel free to go on prothesis. But of course, there's a but, and if neuromorphic hardware and computation are so good, why is it so little used and known? So there is still skeptical people like Yannael, who has done pioneering research in deep learning. And in fact, it has longly been outside of the trend. SNNs has longly been outside of the trends, and most of the time SNNs do not achieve state of the art in deep learning. So this is mostly because there is no real good there is not yet real good algorithm, learning algorithms, and it's complicated to train SNNs, and it's even more complicated to have a learning algorithm compatible to efficient neuromorphic hardware. So you may know that for SNNs, the activation function is a threshold function, and this threshold activation function creates as many advantages as drawbacks. And the major drawback is that it's not differentiable. So the powerful algorithms from ANNs, like backpropagation through gradient descent, are not usable. Plus, there are many algorithms, but there's not one that significantly outperforms the others, like a super algorithm. This makes it really difficult to choose a training algorithm. And I'm not going to present all of those algorithms. Plus, by the way, it's absolutely not exhaustive list. It's just few. This is just few learning algorithms from papers I've read recently. This is just to show that it does exist many learning algorithms. And STDP is a famous one, a famous learning rule inspired from bio-inspired, and I will talk about STDP in future videos, and we can see here that it can be used for supervised learning or reinforcement learning, or also for unsupervised learning. So it's just a learning rule which can be applied to training methods. And yeah, I won't talk about STDP today, but again, future video is just a short introduction. As a conclusion, neuromorphic systems raised attention for lower consumption, but not only, as we've seen in few examples. And however, efficient online learning methods are still required, and there's a lot of research in this field. There's currently a lot of research in this field. As I said before, I provide here some links, the link in case you would like to delve deeper into some topics I've talked about. And yeah, I hope I bring you some knowledge and you were able to enjoy the video. And yeah, I will do a future video about neuromorphic systems and STDP learning. And for now, I say you bye.